Hello, hello. I'm Breton, one of our MCAT tutors here at Inspira Advantage, where we help students get accepted in med school and other professional programs. Today, I'm going to guide you through a robust application of understanding electrochemistry in a biological system. The MCAT loves combining macro topics like chemistry and biology, and that's why I've modeled our guided example work today after the most important galvanic cell in the human body, the ETC. So let's take a moment and read through the prompt here. Mitochondria use the electron transport chain to transfer electrons from NADH and FADH2 through the complexes and electron carriers, as well as to pump hydrogen into the mitochondrial intermembrane space. The reduction potentials for relevant reactions in the ETC have been provided below in Table 1. Okay, so immediately we see that we're given a whole lot of data. We have a whole lot of E cells to work with here. The first thing I recommend doing whenever you're given data on a table is figure out what are some trends that you're seeing. If there are independent and dependent variables, awesome, I'd go for those too. I'm not seeing any here, so I would just look for what trends do we see. So quickly just kind of analyzing the data, it seems like as we proceed down, the number gets up higher. So I'm going to say number increases, just to help me remember as I'm thinking through these next questions. All right, so then, let's look at Table 1. Let's see if we can find any patterns in actually what's being measured. So we see NAD, NADH, okay, so I'm thinking maybe glycolysis. It said electron transport chain, so I'd definitely be thinking electron transport chain. Then looking farther down, we see CoQ. Okay, so this is definitely in the electron transport chain. In complex 3, cytochrome C, and complex 4. Okay, so this is just describing the electron transport chain for us. That's kind of nice. A good thing we want to realize. Okay. And for those of you who aren't familiar, just quickly sketching it out. Oops, didn't mean to get rid of that. We've got our complex 1 here. We've got CoQ floating around. We've got complex 2, which we're not bothering with. That's FADH. We've got complex 3, got complex 4. And in between 3 and 4, we've got cytochrome C floating around. All right, so let's talk about question 1. What type of electrochemical cell does the ETC approximate? So let's just think about our mitochondria. Does it produce energy or does it require energy to run? Well, we all learned it in middle school. The mitochondria is the powerhouse of the cell. The mitochondria is making ATP. Well, it sounds pretty spontaneous to me. If it took energy to make energy, well, we'd be in trouble. So right from there, I know this is going to be galvanic, and that allows me to eliminate C and D right away, because this is clearly not going to be electrolytic. So then we have to dig into the second half of the question, which is normally the trickier part, which is why I save it for the end. So let's look at A. It's galvanic because the physiological concentration of reactants in the ETC cause delta G to be negative. Okay, well, just kind of looking at this, delta G should be negative, so that makes sense to me. Now this physiological concentration part, oh, that sounds maybe a little confusing. Maybe I'm not sure on that, so I'm going to read B to check. Okay, it's galvanic, and delta G will always equal 0 in a physiological system and is irrelevant. B is screaming no to me for a variety of reasons. One of the biggest is whenever I see the word always, I get immediately suspicious. And we know that delta G is not always going to equal 0 as well. This is something that we know to not be true, so it can't be B because of this reason. This is also extreme language, which should make us very wary. So for these reasons, it is A. A is our correct answer. Okay, how about question 2 here? We'll apply what we learned more directly in this one. This is going to be less conceptual, more grunt math. What is the change in Gibbs free energy when electrons move from cytochrome C to complex 4? And is this an energetically favorable reaction? All right, I want you to think about this. I'm going to go back up so you can see see it all at once, take a moment and work on this on your own before I show you how to do it. Good luck. All right. First, again, we have the same structure we saw in the last question. We can either answer 1/2 to eliminate half of the answers right away. So yes or no? I think that's something we want to immediately think about. So change in Gibbs free energy when electrons move from cytochrome C to 4. Okay, well, again, if we draw our little diagram here, if we know where the electrons are flowing from, we know that complex 4, say it's over here, and we know we've got our cytochrome C before it. And if we know our cell biology, we know that the electrons do move from cytochrome C to complex 4. I would think, yes, that cytochrome C is going to favorably move electrons to compound 4. Energetically favorable is just another way to say, is delta G negative? So I'm going to cross off B for no. And then again, thinking along the lines of delta G being negative means it's energetically favorable. There's another answer choice here that screams at me as wrong, which is C. Something couldn't be favorable if it had a positive delta G. That's against the definition. So now we have to do math. Is it negative 25 kilojoules per mole, or is it negative 20 kilojoules per mole? All right, to do this, we need some numbers. So let's find what relevant information. We know that we need our cytochrome C, so that's right here. And we know we need our complex 4, which is down here. All right, and again, from that first video, we talked about, okay, we know we have a galvanic cell, so we need to get a positive E value. We know this because when delta G equals negative NF E cell, okay, and we know E cell equals the cathode minus the anode, and we want E to be positive. So let's do that and combine these two numbers through subtraction to make a positive answer. Well, this one is pretty clear. 0.385 is larger than 0.254, so we're going to subtract them like that. We're going to say 0.385 minus 0.254, all volts. Subtracting this on out, this is going to be some positive number. Now this is the MCAT, so I'm going to round like crazy. I'm just going to say, hey, this is about 0.1, like 3. It's close enough for me. Now we need to plug this into our delta G equation. So let's do that right now. First, we need to figure out what our N is. Well, how many electrons do we have in these reactions? 2 and 2. Nothing fancy, so we're just going to plug in that 2. So negative 2. F is always a constant at roughly 96,000. And then our E cell of 0.13. So now it's time to round. I'm going to round the 96,000 to about 100,000. And then I'm going to multiply the 2 and 0.13 together. So this is going to give me delta G equals 100,000 times 0.26. And this is actually as far as we need to take it, because our answer choices are either 20 kilojoules per mole or 25 kilojoules per mole. And we have something that's pretty close to 25. We've got a 0.26 right here. So if you feel comfortable, you can just pick A right now and move on. If you don't, I'll prove it to you real quick. And if you multiply these out, 26,000, and this would be joules per mole. So divide that by 1,000 to get that into kilojoules. So this is our 26 kilojoules per mole, which is pretty dang close to our negative 25 kilojoules per mole. And my apologies, I dropped the negative sign there. So that's how you would do the math and thinking for question 2. Let's take it up a notch. So this question really tests your knowledge of the electron transport chain, as well as your qualitative understanding of how reduction potentials work. And the MCAT loves broad questions like this. Can you critically think your way through when you're in a tough situation? What must be true of the reduction potential of this half reaction here when we have an oxygen and some waters combining to form H2O? And this should really be written as 1/2. Okay, take a minute, try it on your own first. So again, I'm going to draw that diagram I've been drawing many times today. So, we talked about the first ones. We've got complex 1, we've got 2, we've got 3, and heck, we've even got 4. And we've got our cytochrome C in here. We've got the other one up here. They're moving around. It's actually doing this on through. We've got the one I didn't draw is ATP synthase. So this is the important one. This is actually what makes our energies. So we pump out a whole bunch of hydrogens, make that hydrogen gradient. Hydrogens can then come downstream, combine with O2 to form water. So this is a bit of information that you have to know for the MCAT. You really want to be feeling comfortable in your cell biology. Because again, this is the perfect blend of testing your cellular biochem knowledge and combining it with a difficult electrochemistry concept like redox. So what we call this oxygen down here, we call this the final electron acceptor. So that should give you a clue here, because if we're accepting electrons, that is reduction. Reduction is gain of electrons, oil rig. So if it's gaining electrons, it definitely would be something that loves electrons. The opposite of oxidation. Another way we can think about this is looking at the pattern we saw before. So if we look at our pattern, we said that as we go down, we are getting higher. And this is also as we're proceeding left to right across the ETC. So just based on this pattern, we'd be expecting, oh, okay, well, oxygen is farther to the right on the electron transport chain, and we'd expect it therefore to have a higher E cell. So does anything match our prediction? Lower than complex 4, lower makes that a no for me. Equal to complex 4, maybe. D must be lower than NADH, that definitely won't work. B higher than complex 4. I think higher than complex 4 makes the most sense. But can I prove that to you? To prove it, we would need the E cell values. So to prove this, you could look this up in a table, and you would see that the E cell of oxygen is quite a bit higher than the 0.385 we see in complex 4. I hope this went well for you, and the biggest advice I have for you is to keep practicing these problems. If this isn't making sense right away, rewatch the video, try it again on your own. If you got one of these wrong, that's okay. Use that as a learning opportunity to go back, give it another try. But I want to thank you for watching our video on the foundations of electrochemistry with this guided example walkthrough video on 3 pretty difficult questions. And I'll see you next time.